Electromagnetic induction separate chapter.
This meeting is being publicly streamed.
Yes, yeah, assalamu alaikum. Yeah. Walaikum salam. Yeah, कैसे हो आप? Good. Yeah, Hanzala did not join me till this time. Okay. Should we start?
Okay.
Hopefully. We are at this topic. Yes, Yahya and Zoya, you are both present in the class right now. So we had reached to this point. Velocity sector. Is my screen visible to everyone?
Yes, sir.
Okay. So here we go. We were talking about that. Actually, this point is somehow related to the velocity selection. Velocity selection means when your electric and magnetic fields were placed together, then Walaikum Salam, kaise beta? Yes, we were waiting for you. कि आप आए, लेकिन चलो मैंने रिकॉर्डिंग पे लगा दिया है तो आप देख लीजिएगा. अभी हमने स्टार्ट नहीं किया था, by the way. Okay, so here we were talking about that velocity selector was having a principle that both electric and magnetic field were placed normally to each other, and when a charged particle enters normally to both these field regions, then what happens? That charged particle experiences two forces, electric force and magnetic force, and that electric force and magnetic force are adjusted in such a way that if electric force and magnetic force are equal in equal and opposite to each other, at that time the charge will move undeviated, and at that time the velocity of that charge is equal to the ratio of electric field strength to the magnetic field strength. And if I just replace this electric field strength with delta v by d, because I know the separation between the plates and I know the potential difference across the plates, then it will be delta v by db. So is this all clear to everyone? Anzala, yahan tak clear hai beta? Okay. So today we will discuss, this is the extended topic, the same extended topic, and that is that the velocity selector has an application, and that is basically your mass spectrometer. Okay, there are so many questions from this topic. If yani, although it is not that by the name of mass spectrometer, but these topics, these yani, the questions are asked from this topic. Right? So mass spectrometer is basically an instrument which is used to determine the specific mass, sorry, the specific charge on the charged particles, right? What is its main function, or what is its main purpose? It is used to find charge to mass ratio, right? So it is used to determine the charge to mass ratio. Charge to mass ratio of the particles. Got it? Charge to mass, yani Q by M is actually charge to mass ratio, or specific charge of the charged particles. So what was the reason for finding it out? Because there were some charged particles which were having the same charge, but we were not able to identify, differentiate the charges. So that is why charge to mass ratio was used to differentiate the charged particles. Okay, differentiate the charged particles. So this was actually the main reason for this, or which was this was the main objective of this setup. And it has two chambers. One chamber is basically the electric chamber, and the second one is the velocity selector chamber. For example, I will not talk about in detail about the velocity selector chamber, but in fact the velocity selector chamber has importance on its own. For example, this is that region of the uniform magnetic field and a charged particle is entering in that region of the uniform magnetic field, then what will happen? That charged particle, yeah, this is yani this part is basically the part of velocity selector. The upper part is basically the part of velocity selector. This one, okay, that part is what? That is your velocity selector. This one, the upper part, velocity selector, right? So when a charged particles enters in this region, when it is driven by the velocity selector, here it has certain velocity, then what will happen? This charged particle will create, or this charged particle will experience a drift. For example, if I have a uniform magnetic field region here, I will just draw few crosses in this. All this is the region of uniform magnetic field, and this uniform magnetic field region will decide the, or that will basically cause the deflection of this charged particle. Now if I say that a charge is entering here, and that charge is, let's say, a positively charged particle. What is that charged particle? That is a positively charged particle that is entering with velocity v. So where will be the force acting on this charged particle? We will determine the force on this charged particle. It would be acting towards left. So this sorry, towards right, this charge particle will strike here. At the same time, if I have another charge particle with different charge to mass ratio, then that charge particle will hit this main chamber at this position, and so on and so on. So this is how, you know, this is actually that these all particles which are striking here, they have different deflections, isn't it? They have different deflections. So when they have different deflections, actually you can simply say that yes, due to their different deflections, we can find out, or we can say that this is your charge particle A, this is B, this is C. So all of these charge particles are having different paths or directions of, or you can say that the deflections. Let's say this is Ra, let's say this black one is Rb, and this blue one is Rc. So all these charged particles have different deflection. So here the method or the concept behind that is, because I described this all, that when a charged particle is a magnetic field, so it will experience a force, and that force will keep it moving in a circular path. So that is why in chamber A, yani in the velocity selector area, the physics or the maths is, in velocity selector, as I told you, that velocity is equals to E by B. But in the magnetic chamber, that is a magnetic field only, what happens? Your FC is caused by FB, and if I further explain that, that FC is equals to mv square divided by r, and that equals to q v b sine theta. I have explained this also. Actually, the same concept is there, what we have learned in the last discussion. So here, m and m will be cancelled. Sorry, v and one of the v will be cancelled out, and you will get the equation. And one more interesting thing, that the angle is 90 degrees. So theta is equal to 90 degree, because charge is entering 90 degree to that. So you will get mv is equals to r bq, and here your velocity is E by B, that is equals to RBQ, and that means that if I just shift this R on this side, 1 upon R is equals to B square Q divided by M times E. Is it? Are you getting my point? Is it the right equation? R will be shifted here, B will be multiplied, so B square, and E will be, yes, beta? Clear? Okay. So,
Yes.
okay. So, yeah, is not clear or clear?
Clear.
Okay. Now, depending upon the situation, you can consider the equation for the selection. This is quantitative analysis. So you can have any data. You can be asked for anything to extract it out from here. You can be asked to derive any expression. For example, if I say that derive an expression for the magnetic flux density, so it would be your mv divided by q r. Okay, is it none? Mev, sorry. No. It is me. Is it me? Me divided by m into e divided by r the qb. So you can take square root on that, and that square root is basically this way. So because it is b square. Moving on, it is not a big deal. Lulu, welcome to the class. Okay, so this is one of the equation. Most important thing that when you will replace this e here, e is basically equal to, what is your e? Your e is equals to delta v by d. So I will just rearrange my this equation. 1 upon r is equals to b square divided by delta v into d whole multiplied by charge to mass ratio. Got it? So in the previous topic, I told you that this 1 upon r is basically the deflection, isn't it? R, that 1 upon r is the deviation. So that is equals to b square d divided by delta v into charge to mass ratio. So simply speaking, if I keep all these factors constant, all these factors as constant, then the deflection again, that is directly proportional to deflection in the mass spectrometer, that is directly proportional to charge to mass ratio. So actually, when you are going to calculate charge to mass ratio, that charge to mass ratio equals to, you can make a equation, because as I have told you several equations, but what was the main target for me? The main target was charge to mass ratio, isn't it? Charge to mass ratio. So I will make that charge to mass ratio as a subject here from all these equations. So if I want to, or if I'm interested in charge to mass ratio, that is equals to, from this top, delta v divided by r b square t. So by using these facts or these mathematical tools, you can even find the charge to mass ratio of different particles. Is this clear to everyone? Okay, so okay, now moving onward, this was the mass spectrometer. So qualitative analysis are that if you have a setup like in which the charge to mass ratio is given to you or deflection is given to you, so this equation will be helpful for you to have qualitative analysis, that if there is a charge with double the speed or double the mass, then what was that yani, what will be its charge to mass ratio, or how its path would be determined. So that all I have told you in this topic here, the same concept will be applied. Okay, is this clear to everyone? So this is the same
Yes.
thing. So there is not a big deal. Actually, just the mass spectrometer question is different. So all rules are same as that the charge entering in the magnetic field, yani the entire magnetic field, right? That is why I will wind that up right here, and I will move to another very, very important topic, that is your Hall's effect. This is the last topic of your uh, magnetic forces, and then I will be moving towards the electromagnetic induction. But before that, we will practice some of the questions. Now, Hall's effect is basically, acha Hanzala or Zoya and every other student, when we have the test on 27, 28, Zoya. Okay, so okay. So check it out, and whenever there is a test, so that will be from the topics what we have studied. Okay, when 28, yes. So till 28, inshallah, we will have we have mm, plenty of time, so we will make some more discussions, inshallah. Okay. Now about Hall's effect, I would like to add some points to you, and then I will tell you about its physics. Halls was a scientist, a very young scientist, and he was basically awarded for this work. That is very important work. What we are going to discuss right now, that effect or that observation and the uh, working on that Hall's effect, or this effect, what was later on named as Hall effect, it helped the scientist to figure out the magnetic field strength by with the help of current and voltmeters. Otherwise, they were not able to figure it out. But how that all happened? Yes, just give me 5 minutes. I will explain a diagram to you, and with the help of that diagram, I will continue my topic. Let's say I have a slice of a material. Okay, this is a material, and it's um yeah, this is a material, and that material is having this structure. This is a slice of the material. I will make this diagram simplified. Actually, this is a 3D diagram, so I will try to make it simple plain diagram also, but just a little while after. Okay, this is the slice, and that slice is exposed to a uniform magnetic field. When it is exposed to a uniform magnetic field, the magnetic field lines are from top to bottom. Okay, and that means that here these magnetic field lines will be basically moving on throughout its throughout its slice, and it throughout this area. So it's simply, you can even let me simplify that diagram for you. Okay, there are uniform magnetic field lines. These magnetic field lines are from top to bottom. Okay, and these uniform magnetic field lines tells us about that, yes, there will be a sort of magnetic effect taking place here. Now this is a uniform magnetic field, right, top to bottom, and there is a current entering in this slice, or there is a there is a current which is flowing through this slice. Okay, here I will draw it here. because it will occupy more space, right? The current is entering in this slice from right to left. Okay, ji? Right to left. This is the direction of the current. Now, huh, that that diagram is really interesting diagram. Basically, when the scientists, they just connected a voltmeter across these two ends. That is why I was going to draw. Okay, just give me a second. That diagram is quite important. That is why I will try to draw its complete 3D setup. This is the diagram, right? Now, did you see those rare face, that rare face that I drew, that is with dim ink colors. So that is your rare face. So that rare face and that front face, if you join these two faces, yani, if you just connect a voltmeter between these two faces, then there was an astonishing fact that was observed, and that was that here is a wire. I have placed a wire from this end, and that wire is connected to other face. There is a voltmeter, and this voltmeter is basically reading some voltages, and these voltages are called your Hall's voltages. Did you did you understand the entire mechanism of your diagram, that through
Yes, sir.
which phases I will get the voltages, and through which phases I will get the electric field, and through which phases there will be a sort of, yeah, this is how that it seems that, okay, the voltmeter is connected to this edge, this phase, and here the voltmeter is connected to this phase. These are the two phases at which you have connected the voltmeter, and that voltmeter will tell you about the reading. So here I'm just going to give some values. This is I, this is your uniform magnetic field strength B, and these are the Hall's voltages. Now, the situation is this slice is basically of several values. For example, here, this is the thickness T, this is the this dimension is D, and this dimension is basically L. So I will write the dimensions, all dimensions about this. This is your T, this is your D, and this is your length of the slice. Is this all clear? Now, what is observed basically when a charged particle which enters from that side, from here, this charged particle is drifted by the magnetic field. That charged particle is drifted by the magnetic field in such a way that it will appear on one of the faces. For example, which face? Let's say if it is a charged particle, so what do you think? Where will it go, or where should it be drifted according to this diagram? Out of the page, or into the page, or where? Should I name these faces? This face is A, B, C, and D. The other side is, let's say, E, F, G, and H. Okay, now is it clear to you? So these all faces are named. So my question is, where will this charged particle be drifted when it is entering from right side to the left in the presence of this uniform magnetic field. So where would be drifted? Towards the face ABCD or EFGH? Yes? Yeah, who will tell me? Yeah, yeah. Where will this charge
Yes, sir.
particle be drifting?
Okay.
Okay.
Into the page. Into the page.
EFGH?
Yes.
Okay. Okay, hold on. Let's draw another diagram for you. Okay, don't worry. I will just make this concept clear to you and then I will move forward. I have no issue at all until unless this is not very clear to you. I will not consider that I should write about that. First of all, this is another diagram. This is the top view, right? The magnetic field is basically okay. Now this is the magnetic field. This is the new dimension of the same slice, but in a different way. Now the magnetic field lines are sorry, the current is in the same way. The current is entering in the same way from your right to left. This is the current, yani a positive charge particle, and that will be reaching to this point, right? Now, what is the magnetic field? This is the game, actually. The magnetic field lines are into the page. Got my point? There is, yani, I am just drawing a cross here. The magnetic field lines are into the page. Okay, ji?
Yes.
Yes. The magnetic field is into the page. So, what do you think? What will happen?
Okay then. Um, then force will be up. No, no, not force, my bad.
Okay, okay, okay. No
The
problem.
induction. My
Induction
bad.
will be upward. Now, is
Yeah.
it clear?
Yes.
Okay, there is a positive charge entering from this side. There is a positive charge particle entering in the uniform magnetic field, where the magnetic field is into the page. So where will it be drifted? This upper face is A, B, C, D, and this is E, F, G, H. Now tell me, to which side
This
it
will be
should go?
to
The magnetic field is into the page. This is the
the current.
magnetic field into the
So the
page.
current goes to like induced current, right?
Yeah, and no, no, no. It is basically the positive charge particle entering. The particle charge particle is positive charge particle.
Okay.
Okay. Yes. Go ahead. Hanzala, Walid, everyone, whoever is in the class, the question is with all of you. Is Lulu in the class?
Yes, sir.
Oh, welcome. You can also tell me that where will be this positive charge going by applying the magnetic field concept, or by applying the law of magnetic field, or the concept of magnetic forces. Where will be the force acting on it? Dekho, just use your left hand rule, just point your finger into the page and sorry, index finger into the page, and your middle finger from your right to left, you will see that the force on the charge is downward. So your positive charges will be drifted down. All these positive charges will be drifted down. You got my point? And as a result, all these yani, this side is considered as negative. So the upper face will be considered as negative. This is simple understanding. That is that if the lower face is getting positively charged, yani lower all this positive charge, this is the positive charge particle, so it drifted down. This is the positive charge particle, positive charge particle. All these are your positive charge particles. Got my point?
Yes, sir.
So if this face is now positively charged, the upper face is now negatively charged. So can I say that if one side of this material is positive, other side of the material is negative, then there will be a potential difference developed between these two faces?
Yes, sir.
That is the point. Yani if I just connect the voltmeter between this phase and this phase, what will I observe? Yes, yes. Come on. If I just apply the voltmeter between this point, yes, and the other point.
Between those 2 points, electric field.
Sorry, can you repeat? There's a
Electric field.
Yes, exactly the same point. What I was expecting from you all, that is the here is basically the electric field developed, and when there is electric field between these 2 points, so can I say that there will be a potential difference between these 2 points, and that potential
Yes.
difference means that these are the voltages which are basically developed across this edge, and these voltages are called your Hall's voltages. Yani this is that point where I have connected my voltmeter, and that voltmeter reads Hall's voltages. Is this clear? Now the basic mechanism behind this all game is the positive charge will drift downward, whereas that positive charges, they will be drifted this way. If there are two positive charges which are drifting in this way, due to that, what do you think? There is an electric field developed. Is it? There is an electric field, na? From top, bottom to top. Is it? Are you agreed with that electric field?
Yes.
So that actually this entire game is the game of electric field and magnetic field together. So when we have the electric field and magnetic field here at the same position, I can simply say that before uh, the charges deflect down, there was no electric field down the way, but afterwards there is an electric field or electric field strength which is in the upward direction. So when the charge will enter in the region where F electric and F magnetic both are there, then what do you expect? What will happen to this charge? Hmm? What do you think? This is the electric field, na? Should I write that this is your electric field? So now the charge, the drift on the charge will be decreased. And for example, at any instant, when this positive and negative charge, this charge is experiencing a force. This is an instant. Then these two forces, one is the magnetic force which is bringing this charge particle downward, and the other one is the electric force which is trying to bring this particle upward. These two forces are now balanced and in equilibrium, and when these are in equilibrium, I can simply say that the charge will move undeflected. Right, what will happen to this charge? The charge will move undeflected. Here is that concept, that this is your F electric and this is your F magnetic. You got my point? So that's it. Whatever you have observed here in this entire game or in this entire discussion, I would like to address that all in words here, because the working principle is asked to you. Working principle. I will write all that working principle with in points, so you people can link them all bit by bit. When a thin slice, I will tell you about all these parameters what I'm using. When a thin slice of a semiconductor material is placed normal to the magnetic field, uniform magnetic field you can say, or magnetic field, and a current flows through the slice, a current flows through the slice or that material due to charge carriers, due to charge carriers Q. Here I will just a thin slice, you can say, of thickness T, of thickness T. I will write these all letters again, but here it is important to mention them. Okay, the slice due to the charge carrier, current flows through the slice due to charge carriers Q. A force is experienced by charged particle normal to the current and magnetic force, magnetic field. Is this point clear to everyone? This causes
Yes.
a drift on, drift to the charged particle, drift to a charged particle normal to the current and magnetic force or magnetic field. Is this point also clear? It's the same point, but I have just mentioned in another way that this causes a drift to a charged particle normal to the current and the magnetic field. And charge moves to or reaches to one of the faces of slice. Is this all clear what I have mentioned in my diagram explanation? That moved to on one face of the slice. This causes an electric field to be developed between these opposite faces. This induces, rather I will write one more sentence addition. This induces the this induces an opposite charge on the opposite face of the slice. Got it? Hence, an electric field is developed between these two faces. Hence, an electric field is developed between, yes. Oh, अभी अभी गायब हुई है? Okay, okay, okay. Actually, my meeting was gone. Hmm. Just a second. Yeah, yeah. Do you hear me?
Yes, sir.
But my screen is not being shared. Just give me a second. Some problem is there with my internet, maybe, or with my tab. Ask to join. Yes. Okay. Page is join now. Okay. Okay, now my voice clear to everyone, and my screen shared to everyone.
Yes, sir.
Yes,
Oh,
sir.
okay, okay, okay. And Zoya and Hanzala, is it also shared for you? Yes. Okay. Yes. Sorry for this inconvenience. I was saying that in the charges induced electric fields is developed between these two faces, and this causes an other or an electric force on the charge normal to, sorry, opposite to, it is not normal to. This is the electric force, not electric field. Charge opposite to the magnetic force. Now, when these two forces, when both the forces are two forces, the electric and magnetic becomes equal and opposite, forces become equal and opposite, the charges move undeviated. Okay, this causes a potential difference across two opposite faces of slice, and these voltages are called Hall's voltages. Okay, these voltages are called Hall's voltages. This is very, very important. I have just written entire detail. Now I will just give you a summary that what happens in step number one. This is a summary. This is just for your easy going, uh, memorization. First of all, what happens? First step is charge enters. Okay, charge enters. Then what happens? Magnetic force exists on the charge or appears on the charge. Magnetic force. Due to that, drift causes in the charge. Due to that, due to this drift, faces are oppositely charged. Faces are oppositely charged. This causes electric field induction, or electric field induces. This causes a potential difference between two phases. That's it. And those are called Hall's voltages. Is this summary clear to everyone?
Yes, sir.
This summary is basically a short summary, but I believe that that will help you out to understand the entire concept. Okay, the charged particle enters in the magnetic field where magnetic force acts on it. It causes drift, and that drifts in opposite phases. And the charged particle, that is why the opposite charges are induced on these two opposite phases, and electric field is developed. And due to that electric field, what happens? There is a charge. There is a potential difference, and that potential difference is called as Hall's voltage. Is this clear to everyone? Any confusion in this all?
No, sir.
Okay, so the this is one of the aspects. So this all principle of Hall's voltages is asked to you. Although I have written it in very strong detail, but that is asked to you. That is why I just did that all. in front of you. Now here is, this was the diagram. So as I told you that the positive charges will appear on that side and negative charges will appear on the other side, isn't it? So I was asking to you, but you people did not answer my question, that what will happen to the positive and negative charges. So this phase will become negatively charged, and when this phase will become negative charge, negative and positive charges will cause an electric field induced between these 2 points. And when that electric field is induced between these 2 points, basically it shows you that yes, this is the electric field. Okay, this is the electric field. Is it clear to everyone? Got it? So the important thing here is where these yani the phase where the electric field is developed, that is actually um, that phase is what, sorry, that phase is what, that is the phase which is sorry, that is the distance d through which the magnetic field passes, it is t, and through which the current passes, it is your l. Okay, so here these three notations are very important: t, d, and l. What is t? Thickness of slice, where thickness of the slice means the length through which magnetic field, or you can simply say that is the length parallel to magnetic field. So can I simply say that t is parallel to the magnetic field? Isn't it quite easy? Any side parallel to magnetic field, that is t, whatever that is, but that is t. That is basically the breadth of the slice, breadth of the size slice, and that is actually parallel to electric field. You got my point? Is this very clear to everyone? And this is length of the slice, and that is parallel to current. Never forget these three things. They are very important because they are asked to you in your exam, that yes, how do these all differ from each other? Okay, till this point, any confusion? Huh? Any confusion? Okay. So till this point, I will wind up this class here. Unfortunately, it is a long topic to go. I will just write the formula of the Hall's voltages, and I will perform the derivations in the next class, inshallah. So Hall's voltages are equal to IB divided by NQT. This, its derivation is asked to you. Some qualitative analysis are also asked to you. So hopefully it will be clear to you. If not, then ask me whatever or wherever you are having some issue. Yes. Is there any issue or anything you want to ask me? Okay. Do you people have some class ahead?
No, sir.
Yes, sir.
Okay. Lulu, you have a class ahead?
Yes, sir.
Oh my God. Okay. Okay. So yes, inshallah, we will be discussing that all in the next class.
Okay, sir.
Okay. See you then.
Thank you, sir. Bye, sir.
Welcome. Okay, ji. Allah Hafiz, students. If you have any question, you people can ask me.
No, sir.
Not at all.
Not yet.
Okay, okay. So I am expecting that there will be some questions, right?
Eventually, sir. I mean, once I do the past papers.
So when are you going to do past papers?
Probably the weekend.
Okay, I will be expecting that you are doing past papers. Okay, ji. See you inshallah. Allah Hafiz, everyone.
See you, sir. Allah Hafiz.
Allah Hafiz.